chapter, and I'm pleased to have you all, whoever is here on the telephone or on the webinar for today's presentation. We're going to be hearing from Doug Merrill from Sunward Systems, who is going to be telling us about what we've learned about solar hot water systems, the monitoring we've seen, and how that's indicated how it's working. And I'm going to hand it off to Doug. Welcome, Doug.
Thanks, Chris. Thanks for having me here today. I'm going to scroll down here. Page down. Okay. There we go. Okay. So this morning, Chris and Peter Schneider asked me to talk a little bit about primarily what we've learned installing solar hot water systems, particularly with particular respect to their application in passive homes. But to do that, I was asked to give a little bit of background into solar hot water systems in general, how to integrate them into a home, and give a little bit of a lesson on sort of some of the differences between different designs of solar hot water systems. So we'll start off with that. I'll talk about myself, go through some of the advantages of the system, discuss the differences in the systems, and then talk about some of the lessons we've learned in installing these in over 500 conventional homes and several passive homes over the past couple of years. So my background is in manufacturing and engineering. I started with GE, spent a lot of time at GE Energy. Also worked with Husky injection molding, and then spent a fair amount of time doing some consulting and teaching at UVM. My experience with solar hot water goes back about 4 years. I started as a consultant for supply chain Sunward Systems, and through that got involved in how solar hot water systems are designed and built, and also got involved in monitoring them for performance, which is how I came to know Peter Schneider, and which is primarily why I'm here. At the beginning of this year, I came back to Sunward Systems as a co-owner and the COO, so I'm involved there. I'll do my best to make sure I'm not biased in how I talk about solar hot water system components, but if I am biased, I'll try very hard to identify that bias. But I'll discuss all systems, and these are not going to be Sunward-specific comments. Okay, so solar hot water system advantages. Most of them are pretty easy, and I think just about anybody who's listening to this webcast will know most of these. The first is that it reduces the need for electricity or fossil fuel. Those are the primary ways with which we heat hot water in the U.S., and if you have a solar hot water system installed on a home, it's simply going to reduce the amount of those primary fuels that you need. We reduce those fuels for a variety of reasons, for environmental reasons, carbon reasons, but a lot of people will reduce them simply to save money. And these systems do save real amounts of money. The other advantage that solar hot water systems have over other hot water heating systems are they're easy to integrate. And we'll talk more about that a little bit later. When we think about passive houses, one of the advantages a passive house is going to have in ease of integration is, by definition, they're going to have good solar exposure. So the only reason the solar hot water system won't work is if you don't have solar exposure. That's not going to be a factor in properly designed passive homes. The other factor with passive homes is domestic hot water energy needs are a fairly high fraction of a passive home's energy requirements. So by making your hot water heating system draw less energy, you're going to reduce the overall energy need of that house substantially. This is borne out by a chart that I borrowed from Peter Schneider, which shows that domestic hot water heating is typically the second highest building load after building heating itself. Building heating is the highest. Domestic hot water heating is the second highest. In most homes, it's probably about half the load of all of the other household uses: lighting, computers, electronics, things like that. So it's a problem we're solving. It's a substantial load, and as you make the home more and more energy efficient, the percentage of power that is represented by domestic hot water heating rises and rises. It becomes a more important problem to solve. So how do we heat hot water if we don't have a solar hot water heating system? Oh, sure. scroll down once. There we go. So the primary way we do this is with electricity. We can use a resistive heating as a conventional electric hot water heater in a storage tank, or in an instant hot water system, or heat pumps have become more popular over the past couple of years in some areas. If you don't use electricity, you're going to use a fossil fuel, propane, oil, or natural gas. The nice thing about solar is no matter what fuel you're burning to make hot water, solar hot water heating can offset and replace a substantial fraction of that primary fuel source. So some of the advantages, as we mentioned, it saves money. It's a good investment. So how good? If you look at a return on investment for a solar hot water heating system, what we're finding is that the two factors that influence the return on investment are how many people are in the household, which directly influences how much domestic hot water you use, and what is the fuel source that you're heating with today, and what does that cost. In 2012, propane is fairly expensive. So for a family of 4, if you were burning propane to heat your hot water with an average sort of efficiency on your burner, you're going to see about a 9% return on investment when you invest in a solar hot water heating system. For oil and electricity, they're about 7%. Natural gas right now is very cheap, so you're going to see about a 3% return on investment. That doesn't sound great. I mean, they're all single-digit numbers, but when you compare them to any other financial investment that you're going to make, they're pretty good. If you're looking at putting money in CDs, things like that, these investments are pretty sound. So these aren't just ways to heat your hot water. You have to compare this to the alternative, which is doing nothing. And this investment is actually a pretty sound investment. We have a question. The tools we use, when we're looking at these systems, we can look at any one of those systems, so direct fire, storage, things like that. What I was looking at here, I believe, are the most common systems we see here in Vermont. And so for oil and gas, they're generally an indirect fired loop off of a boiler. Electricity, it's going to be a standard resistive electrical hot water heater. Propane, I believe, they're generally standalone direct fired. So these are the most common systems we see here in Vermont. But it does make a difference, obviously. Once again, these systems make good sense if you have 3 or more residents. The challenge is that when you get down to 1 or 2 residents, the systems still work. They still offset hot water usage. However, the water usage itself is so low that the initial cost of the installation makes the ROI drop pretty substantially. So from a financial point of view, they become less attractive when you get down below 3 residents, 1 or 2 residents. The other thing to think about in New England is if you're trying to offset sort of conventional fuels, we don't have many really good alternatives to do that. Heat pumps are sort of up and coming, but from what we've seen, unless you're going to be running a cooling load for a large portion of the year, they're not a particularly efficient way of heating hot water on a total system. Wood is great in the wintertime, but if you're going to run a wood boiler in the summertime, it's an awful lot of work, and it's not particularly efficient. So in fact, if you're heating with wood, solar is a great sort of counter-seasonal complement to that. Okay, we'll talk a little bit about ease of integration. So when you're putting up a house, or a passive house, or any other house, solar hot water is actually a very, very simple system to add to almost any house. Part of the reason it's easy is because the collectors aren't nearly as sensitive to position and orientation as photovoltaic. So a lot of people get confused about that. I continue to be amazed at how many people confuse sort of the physics of photovoltaics with the physics of solar thermal heating. And whereas photovoltaic panels are very sensitive to shading, to partial shading, the drop-off rate is fairly high as the sun drops off at the normal incident angle from the collectors. Partial shading for a solar thermal panel really isn't a factor. If you shade 10% of the collector, you're going to get 10% less power, not 90% less. And the energy drop-off for most collector technologies, when you get off normal, is not that rapid. So we've got a lot more flexibility in where we mount the collectors and what we have to do to the surrounding sort of landscape to make sure that these are going to be efficient systems. Panels can be mounted on the roof of the structure. They can be mounted on the ground. Most of the time, you're simply preheating your water going to an existing hot water heating system. So the physical integration into the home's mechanical systems is pretty easy. You're going to basically divert cold water going into your existing hot water heater and into your solar hot water heating system, and then feed that. So you don't have water going back and forth. You don't have kind of these funky feedback loops that you get in some systems. It's pretty easy. What that means is that you have very minimal building and design compromises. You're very flexible in terms of what domestic hot water systems we can work with. And the nice thing is we've got a pretty small footprint in the home for mechanical systems. So as I said, we're pretty robust on how to mount the collectors. Obviously, collectors that face true south are ideal, but the follow-up in production is pretty gradual. We will recommend installations that even go as far off as 45 degrees from true south. One of the nice things is a lot of times we get questions saying, well, why don't you have a tracker option like we have on photovoltaic panels? And the answer is because it's really not needed. The production doesn't fall off that quickly. The added cost, the added maintenance simply wouldn't justify the extra production value. So we're pretty flexible on alignment. Partial shading is fine. As I said, if you shade a couple percent of the collector area, you're going to lose a couple percent of production. Small features like power lines, branches, things like that aren't a factor really at all. What you're looking for is 5 to 6 hours of direct sunlight a day. So even if you've got a big tree that's shading you for an hour or two in the morning in the wintertime, that's not going to be a huge factor. It does not have to be a perfect site. Most of our experience is in mounting on roofs. Most people find a roof mounting to be the most cost-effective and integrates the best with their landscaping and their home. Collectors should be mounted at pitch basically equal to your latitude. So in New England, we're looking at about 45 degrees. We recommend that if it's easy to go steeper rather than shallower so that you get better production in the wintertime when you really want the most energy. And you lose a little bit of production in the summertime, which isn't a factor because these systems overproduce in the summertime anyway. So if you can get it up to 50 or 55 degrees, that's better in New England. It's also going to help shed snow, so which is definitely a factor here. You can add incline kits to just about any collector to increase the angle if your angle is not steep enough. Most of this is common sense. Anything you're going to use to fasten to a roof must be well sealed. We recommend full flashing on the installations. Tubing and wiring, the cleanest way from a visual point of view is to penetrate the roof and go down through the attic or the eaves. If it's a new house, it's very nice to run tubing and wiring through the walls inside the house. But if it's not a new house, there's really very little efficiency loss. It's more of an aesthetic issue to wrap the tubing and wiring around an eave and go down the outside of the home. So one of the things to take into account on a roof mount system is to review the total rise of the system. And by that, I mean the distance from your glycol pump to your collectors. Some systems are very sensitive to that and will place pretty strict limits of 25 or 35 feet. Other systems are not. And we'll give you a tubing run and tell you basically can go as high as the tubing run could be 100 feet, 120 feet. So if you're going up on top of a two-story home and you've got a basement, you may well have a rise of 35 or 40 feet. You need to make sure the system that you're looking at is rated to handle a glycol rise of that level. And where you really ought to look at that is if you're looking at larger diameter piping going up to the roof, and you get into the 1/2 or 3/4 inch diameter piping, the glycol weight begins to become significant, particularly if it's a drain back system. And the pump is going to struggle to, you need an oversized pump to get the glycol up to the roof. When you're looking at systems with very, very narrow tubing, particularly if they're closed, generally speaking, they're not going to limit the height of the collector from the heat exchanger. So if I have any other notes on that, I think I did. If you've got a roof line that simply is not going to support a south-facing orientation, ground mounting is a great option. There are fairly inexpensive racks available that get anchored down to the earth, or you can mount on a shed. Some manufacturers like Sunward sell sheds for this purpose, but we've also seen numerous cases where people have a chicken coop or a shed in the backyard where we can simply put collectors on that and run the copper tubing and the wiring through a trench. And on this slide on your left, you can see we've got a trench dug out to that garden shed where there are collectors on the back. And you can see the other view of that shed on the right, right there. As you can see, those collectors are facing south. That farmhouse has an east-facing roof and a west-facing roof, and no roof even remotely facing south. So ground mounting was really the only option to get enough surface space to heat their hot water. Obviously, the ground mount is going to be lower than a roof mount in almost every case. So shading becomes more of a factor looking at vegetation. So you really have to take a look at the vegetation that's there. Look at make sure that in the late summer, early fall, once whatever vegetation is in front of that is grown, how high will that be? And make sure the homeowner understands that that may have to be cut back every year or two to make sure that the system does not get shaded. Generally speaking, positioning becomes much more flexible once you go to ground mount. You really can be anywhere within 100 feet of the home, and it becomes a factor of both shading and the homeowner's preference as to where the system is located. You've got great flexibility. You have a little bit more expense. And the extra expense comes not through high-tech materials or anything like that. It's basically just labor. You've got to dig a trench that's 50 or 100 feet long. We recommend at least 18 inches deep. If it's going to go under a driveway or something that's going to have heavy, regular vehicle traffic on it, you probably want to go deeper. So that's just labor. And you also have to build whatever structure, and anchor whatever structure is going to hold these collectors in place. So you've basically got a day of digging a trench and erecting a steel frame or building a shed. And that is what causes the extra cost. On the plus side, you do save the cost of getting ladders or scaffolding up on the house and getting the collectors up on the roof. So there's a little bit of an offset there. But in general, the ground mount tends to be a little bit more expensive, $500 to $600, maybe $700 more expensive than a roof mount system. Okay, so now that we know where to put the collectors, how do we integrate these collectors, the system with with your existing domestic hot water heater? So as I said earlier, generally speaking, most of these systems, your solar hot water heater is going to act as a preheater. So cold water is going to flow into your solar hot water storage tank. Your solar hot water heating system is going to act on that storage tank, transfer heat to it from your glycol, and then that storage tank will get hot, or at least warm in the middle of the wintertime, and that's going to go into your backup domestic hot water heating system, which will then deliver it to your house. So in the summertime, you're going to deliver 160-degree water into your domestic hot water heater. Hopefully your domestic hot water heater is set so that it's not going to try and heat that any further. That's plenty hot. That'll be tempered down by a mixing valve into your household. It will deliver water 115 to 125 degrees. In the wintertime, at least here in Vermont, there are going to be weeks where you're not going to see 160-degree water. You're going to see 80, 90-degree water, things like that. So that'll go into your domestic hot water heater, which then has to heat the water from 80 or 90 degrees up to 125 degrees, as opposed to 55 degrees where it's coming from the city or out of your well. So even though it's not covering 100% of your needs, you're still reducing the need for backup energy to heat domestic hot water. We do get questions about, well, if I put another panel up, can I go 100%? And what we found is it's really not cost effective to try for 100% if your expectation is that you're going to have hot water year-round in the quantities that we are accustomed to using. And the problem with it is not collection capacity. The collectors are relatively inexpensive. It comes down to storage. In the wintertime, you simply are going to have a couple weeks a year where you have very, very little solar energy on the home. We have very, very cloudy weeks. We have weeks where we have a couple feet of snow, not recently, but hopefully soon. And so you're going to have a system where you'll need to have a system where you have several weeks worth of thermal energy stored in order to make sure you've got hot water for showers and laundry through the winter. And trying to store that much hot water and insulate it well enough that it doesn't lose that heat through standby losses over the course of a couple weeks simply isn't cost effective. So we don't really try for that. What we found kind of the tipping point is to aim for covering 65 to 75% of a home's domestic hot water energy needs throughout the year, and that seems to be kind of the point that is most cost effective for most homeowners. I think I covered this before, but solar hot water is fuel agnostic. It really doesn't matter what fuel source a homeowner is using to heat their hot water with now. You can use less of it if you go to solar hot water. That doesn't mean that any home domestic hot water heating system will work well with solar hot water. Some work very, very well. Some don't work as well or efficiently. And there are a few systems that really just aren't suitable for solar hot water, and I'll talk about that right now. The most efficient way to integrate a solar hot water system is to use some sort of storage type heating system. So to have a tank of water in the basement that's getting heated through another fuel source. That could be a conventional electric hot water heater with resistive elements in it. It can be an indirect fired tank where your boiler has got a loop through it. But you've got a tank of hot water, a mass of water that is being heated by another source. What that allows us to do is it allows the heat that we're putting into the system to be absorbed somewhat gradually and stored kind of in a second spot. So it builds your reservoir up for those longer, cloudier weeks. If you don't have that, if you've got an instant system or a tankless or on-demand system, many of those systems are not designed to handle water at incoming temperatures over 125 degrees or so. A lot of them heat to 125, 130, don't have a tempering valve after them. And the modern ones have got safety gear on them that if they see a temperature of over 125, they flash a warning. If they see a temperature of over 135, they shut down for safety reasons so they don't scald anybody. And so if you're using a system like that, you need to have a tempering valve after the solar hot water storage tank and before the on-demand system, which reduces the efficiency. So you're basically mixing in cold water with your solar heated water. In the summertime, that doesn't really hurt anything because you've got so much energy in the tank anyway. But in the wintertime, you're taking water that's heated but not hot, and then you're mixing it down and making it cooler. So you're really losing some efficiency in the wintertime. So if you don't have to do that, if you have a storage type backup heating system, your overall system efficiency is going to be higher. Now, while the systems work well with indirect fired storage systems, one of the things we've learned, and it took us a while to figure this out. I don't know how many people have thought this through. Peter and I actually kind of puzzled this out and really nailed it after we got some monitoring done, is that indirect fired systems are much, much less efficient in the summertime than most of us understand. And this question? Okay. And that's because in the wintertime, if you look at the nameplate ratings on these heaters, you'll see efficiencies of 70 to sometimes 90% for newer heaters. And I think those are true under basically full load conditions, under normal operating full load conditions. And so in the wintertime, when you're heating your home and the system is cycling normally, your hot water is being heated fairly efficiently, at close to nameplate rating. In the summertime, when your home is not, when you have no heat load for that boiler other than your domestic hot water, that boiler basically is going to either shut down and have to completely reheat every time you call for heat, or you're going to have to keep that boiler core warm all the time. And what we found is indirect fired domestic hot water systems are operating at efficiencies in the summertime of well under 50%. And it took a lot of looking at data to really understand that and start getting at why that was. Because basically what we were seeing was we were burning a lot more oil or gas in these indirect systems in the summertime than the domestic hot water energy needs calculated out to be. And after looking at 4 or 5 homes and realizing that this wasn't a measurement error, we saw this in every home that we monitored that had a hot water heated with an indirect system. it finally dawned on us that we were basically, for every BTU you use to heat your hot water, you're using another BTU just to heat your boiler and its water circulation system. What that means is that indirect fired systems really do well. I mean, they benefit much more from the solar hot water system than the traditional calculations will tell you. Because if you start plugging in the typical efficiencies into these boilers, they're going to give you a savings, an offset. But really, you're offsetting a lot more because these systems are just so much less efficient in the summertime than the numbers indicate. And I think I mentioned before, when we go to on-demand or tankless systems, modern systems will work. Most of them require a tempering valve upstream of them before they go in. You have to be really careful looking at older tankless systems that are going through boilers, because a lot of those fire whenever they see flow. And so when you look at systems that are 15, 20, 25 years old, as soon as you turn on the hot water, that boiler fires and just increases the temperature by a certain amount. So you're not going to save anything if you put a solar hot water system in. And in fact, you may well be creating overheated water. You're going to start blowing pressure leaks out. So before you retrofit a system, it won't be a factor in a passive home. But if you're involved in a solar hot water installation and you've got an older tankless boiler, you've really got to do your homework and make sure that it's got a temperature sensor in it so that it will not fire if it's seeing hot water being delivered to it. Okay, so utility room needs. This is a significant factor in passive homes, because passive homes, by design, are generally speaking fairly small. They want to be very efficient with space. And one of the first areas that seems to shrink in these homes is the utility room. And the utility room often becomes the utility closet, sometimes under the stairs. And that can be a factor because these systems do require some space. One of the things that makes solar hot water systems work well is water storage. And to store water, you need space. You need a storage tank. So you need a footprint for the storage tank and a heat exchanger. If you use a tank with an internal heat exchanger, that may save some space. We'll talk about that a little bit more. Usually a 2.5 by 4.5 foot footprint for the solar hot water system is sufficient. You need access to an outside wall or a chase for the tubing and wiring. That doesn't mean that the room has to be on the outside of the house, but you have to have some way of getting to the point at which the plumbing and wiring is going to come down from the roof into the basement. If you want to monitor the system, you need data access. You need some way of getting a line to your router from the solar hot water system. It's very tempting to go with integrated integrated storage tank, water heater, and heat exchangers. They're available. You can buy them. You can buy them readily, but they force a lot of compromises. The primary compromise is, as I said before, water storage is your friend when it comes to solar hot water, making it effective. And it's really the cheapest way to make the system perform better, is by adding storage capacity. If you have a single tank, it's very common now to see a single tank, 80 or 115 gallons, where you'll have a heat exchanger coil in the bottom and a resistive element at the top. And that's kind of the one device does it all. It's very slick. It saves space. It can save some installation costs because there's less fittings. The downside is that you're losing a lot of storage that way. You simply don't have all of that space above the resistive element is now basically off limits to solar storage because it's going to be kept hot by the resistive element, and therefore it's not room for your solar heated water to get hot, rise, and expand into. So you're cutting down the storage potential of your solar hot water system. When you have a single tank instead of two, you're going to see some mixing. And what that's going to do is it's going to end up both warming up your solar storage reservoir and cooling down your resistive reservoir, which is then going to cause your resistive element to fire more often and use more heat. And it's going to make your solar system work less efficiently in the wintertime. As that gets warmer, the temperature gradient drops, and therefore your heat exchanger is less efficient. So your heat exchanger is going to pull heat out of the glycol and into the water more and more effectively the colder your water is. So having these combined systems drops system efficiency both on the heat transfer side and on the lack of storage. The other compromise it makes is you end up with, when looking at life cycle costs, a much more expensive system. tanks fail. The solar collectors on the roof will last a long time, but the tanks themselves, just like a water tank, do fail periodically. The more you pay for your tank, the longer it will last, but they're all going to fail eventually. If you have a basic plain storage tank, you're looking at a replacement cost of several $100 for an 80-gallon tank, maybe $500 to $700 down the road. If you go with an all-in-one solution with an integrated heat exchanger and a resistive element, that's a solar-specific tank, and you're looking at a replacement cost of closer to $1,500 to $2,000. So just because of the failure in a tank, you've got to replace a very expensive component in the system. Okay, I want to talk about a couple of differences in systems, because there are some very, very different designs out there. They all work, and almost all of them have got applications where they'll work better than other systems. So there's no bad systems or good systems, but there are different systems, and it's important to know what makes them different, and when their use is optimized. So we'll talk about direct versus indirect, talk about collector design, some heat exchanger information, and touch slightly on drain-back systems and stagnation points and efficiencies. Okay, the biggest difference is direct versus indirect systems. Direct systems will heat potable water in the collectors themselves. So basically, you're going to take the water you're going to drink. It's going to get plumbed up to the roof, where it will be in the collectors. The sun hits it, gets it hot. It comes back down into your system, and you use it in the home. Indirect systems don't do that. Indirect systems keep the potable water inside the home and use a heat transfer fluid, usually glycol, to go up to the roof, get hot, and come down into the basement, where it will then heat the water. The advantage of direct systems is they're very efficient and they're very cost effective. You have fewer components, so they work really well. Water is a better heat transfer mechanism than glycol, so direct systems do work better than indirect systems, all other things being equal. The reason we don't see them used in New England at all is, unfortunately, water freezes below 32 degrees. It gets below 32 degrees often up here. In fact, it was below 32 degrees last night. I was surprised to find. And water expands when it freezes. So it's going to, anytime you have a direct system on a roof, you either can't use it if it's freezing outside, or you have to have very, very robust ways of making sure that the water gets out of the system before you reach a freezing point, in which case the system's not going to run when the system is at or below freezing. So for that reason, indirect systems are much more commonly used in the U.S., and particularly in the sort of the northern half of the U.S. They allow four-season operation. The downside is that they do cost more. You have to add a heat exchanger, you have to have the glycol itself, and the system, due to the lower heat transferability of glycol and the decrease in efficiency through the heat exchanger, the systems aren't as efficient, so you end up having to add some collector area. But for this part of the country, and anywhere near this part of the country, really they're the only systems that make sense. So you really don't see direct systems being used in New England. The only exception I'll make to that is pool heating. So if you've got an outdoor pool and you're only using that pool in the summertime, a direct system will work fine there. And there's no reason not to do that, because you're going to be draining that pool out. You're going to remember to drain the heater out so it doesn't freeze, and so they work quite well in that application. So we're going to talk about indirect systems. That's what we have. That's what I have expertise in, and that's what we see installed primarily here. If you've got a home that's being built in an area that does not freeze, in sort of the Mediterranean, in Florida or Texas, Arizona, New Mexico, California, the direct system will work fine, and that ought to be considered. But I'm not the person to give you advice on it. My experience is all on indirect systems. So with that being said, one of the biggest decisions that most people look at when putting in an indirect system is what type of collector to use, flat plate versus evacuated tubes. Both types of collectors. The collectors are what go on your roof or go on your rack mount system, and they're basically something that's going to be dark, usually a dark gray or a black. Sunlight hits it, as we all know from sitting in a car with black leather seats. Dark things get hot in the sun. That physics has been around for years. It's not going to change, and so both of these technologies work very, very well. They've got something dark that goes in the sun, and it gets hot. and you're going to pass fluid over a portion of this, and that heat that hits the collector, which is going to have some sort of metallic surface, is going to pass through that metal into the heat transfer mechanism, the glycol. The glycol is going to pull that out of the collector and take it down to the basement. As I said, both flat plate and evacuated tubes are very, very effective. What we found is that if you look at a flat plate collector versus an evacuated tube, for total cost, the flat plate collector is going to cost less per BTU generated than an evacuated tube. It's a more cost-effective solution when looking at producing the same amount of BTUs. However, BTUs, evacuated tubes, a lot of proponents say they're more efficient, and they do produce more BTUs per square foot. So if you're limited on the amount of space you have on your roof to work with, or you're really trying to produce an awful lot of power, so it's getting expensive to build racks and things like that, an evacuated tube system is going to produce more BTUs per actual square foot of collector area. Evacuated tubes also can supply higher temperature levels at lower energy levels. Since they're evacuated, and as the absorber gets hot, you're not going to lose as much heat through convection, particularly when it's very, very cold outside, because you've got an evacuated tube. A flat plate collector, even if you put more collectors up to keep the overall energy amount high, the temperature itself is going to drop off. You may get more energy out of it, but the temperature level is going to be less. So if you're trying to generate higher temperatures, for example, if you're trying to work with a baseboard heating system where you want temperatures much higher, evacuated tubes are a more effective technology to use than a flat plate. If you're looking at domestic hot water where you don't want it hotter than 120 degrees at point of use, or radiant floor systems, flat plate collectors are more than adequate. They give you much more than adequate temperature rise to work with those systems. I'm going to have the notes on the two. The other factors that are to be considered are at least in the north, are snow shedding. The very properties that make evacuated tubes perform at higher temperatures, that almost absolute insulation between the hot absorber and the surface of the collector mean that there's going to be no temperature heat radiating to melt snow that accumulates on them. So in New England, that's a real factor. The fact that we do lose a little bit of heat from a flat plate collector in the wintertime is a real bonus. So what we find is that as long as you have less than 6 inches of snow on a flat plate collector, enough radiation gets into the collector through the snow to heat up the absorbers, and over the course of a couple hours, what you'll find is, at least on the bottom of the collector, the snow is going to begin to melt from the inside out. And most often, as long as you're at a 40-degree pitch or higher, it doesn't melt all the snow off, but it does is makes the snow at the bottom very, very wet, and it creates a layer of water, and the snow just slides right off very quickly. Those of you who've seen evacuated tubes in the wintertime know that they create a nice sort of casing of snow around them, and they're well insulated, and they'll be there for quite a while. So those are the primary differences between the two collectors. The other thing to think about is the total cost of the system, including the installation. So evacuated tubes tend to require a substantially more amount of time to install on the roof than a flat plate. Flat plate is like taking a big 4x8 picture up onto a roof. They're very awkward. So getting them up onto the roof can be a challenge, particularly if you're up very, very high. But once they're up there, you're usually going to secure them with 4, 6, 9 fasteners, and they're done. Evacuated tubes are easier to get up onto the roof because you're going to take the tubes up one at a time or two at a time, but you have to assemble them on the roof. And so generally speaking, at least when I'm working on roofs, I tend to drop small fasteners and tools at an alarming rate. And there's a lot of assembly work that has to be done on the roof, and it can be very time-consuming. So that's probably the only other factor to consider when looking at the two technologies. Thinking about heat exchangers, I think I've covered this a little earlier. Internal heat exchangers are very common on particularly tanks that are sold as solar tanks, solar components. There's nothing magic about it. You've got a storage tank, and you've got basically loops of copper inside that tank. I've got them on a picture of a cutaway on the left. Some manufacturers use external heat exchangers. And so basically what you're going to have is a copper coils inside a small sleeve of domestic hot water. you heat up that small sleeve, and then thermal cycling or a circulator pump is going to move that water from the heat exchanger up to the top of your storage tank. That will displace water in the storage tank, and it will drive more cold water into the heat exchanger. The external heat exchanger adds a little bit more initial cost because you have to have the casing, you have to have the extra copper to hold that kind of water. But the nice thing about it is that heat exchanger, if it's well built, is going to last the life of the system, 25 to 30 years. The water storage tanks, if they're glass-lined steel, are going to last the same amount of time as your average water heater lasts. I think they're warranty for 8 years, and we see them lasting anywhere from 5 to 12 years. The real factor here is water quality in the home. Stainless steel tanks last longer, but they're not lifetime tanks. They rust out as well. Eventually, a pinhole is found in some wells, and they'll rust out. They'll probably last twice as long as a glass-lined tank. The challenge, though, is once you start incorporating extra hardware into this tank, when you lose the tank, you lose all of that. So if you have a solar storage tank, the tanks themselves are made the same way as conventional water tanks, so they're going to last about the same amount of time. And if you have a glass-lined steel tank with a heat exchanger in it, when your tank fails at 8 or 9 years, that tank and heat exchanger all go out. The heat exchangers are built in, they're permanently installed, and so the whole thing goes out, and a new one has to be found. The other thing is you need to make sure when you are replacing a tank with an internal heat exchanger that you've got a direct replacement, because not all heat exchangers are the same. It's important to match the heat transfer characteristics of the heat exchanger you're putting in with the one you took out, because the system was designed to all work together. So at the time that tank fails, you need to make sure you have an equivalent tank available, so either the same manufacturer or you've got to do some research to make sure that you're replacing it with the same tank. If all you have is a storage tank, you basically just need to match the gallon, and any storage tank is going to fit the bill. But the internal heat exchanger does make for a cleaner installation. You don't have another box sitting on the floor. So there are pros and cons to each. Before I have heat exchangers. Okay, so that's all I had on kind of the sort of background on how solar hot water systems work, what the different components are. The rest of this is on lessons learned, and the first half of this is lessons learned on solar hot water installations in general, sort of things to look out for, some unexpected benefits, and then the second half is going to be the actual performance we've seen on a couple of on 2 passive home installations we've done in the past 2 years here that have very, very different results because of the resonant solar hot water use patterns. So I've been involved with Sunward, and we've put in about 500 systems over the past 4 years. We've monitored a dozen of those systems to a pretty tight degree, where we're looking at temperatures in and out of heat exchangers, collectors, storage tanks, cold water input. So we've begun to try and really look at what makes these systems work well and how do we make them work better. And how do you get the most out of it? So one of the first lessons we've learned is you really have to look at the full life cycle cost of the system. And that means, what is the equipment cost when you buy it? What is the installation cost going to be? That really depends. Is it the home builder that's doing the installation? Is it a solar contractor that's doing it? Or in some cases, the homeowner is going to do it. And if the homeowner is going to do a substantial portion of it, that may save on the overall cost if the homeowner is not assessing the project his time at a high rate. Installer experience and warranty. What we found is inexperienced installers tend to have to come back to the systems a lot. Hopefully that's under warranty, so that it's not an out-of-pocket cost. But if the system isn't producing properly, you're going to be burning fuel to replace the BTUs that your solar hot water system isn't producing. Warranty is a big factor in this, as I said. I mean, in my experience, the collectors seem to be pretty robust. We haven't had any problems with our collectors. I don't think our competitors have problems with their collectors. Once again, if you put something, if you paint something black, put it in the sun on your roof, it's going to get hot, and it's going to get hot for a long time. So the collectors really tend to be pretty robust. The 2 areas we can see problems are in the controllers and pump assembly, and in the water tank itself. And the controller pump assembly, it's important to have a good warranty on that, because those tend to be very specific to your system. If it fails, you want to put the exact same pump and controller back in. And those are, generally speaking, many hundreds of dollars for a controller on top. It's not staggeringly expensive, but it's not the kind of expense. If you've got to replace it every 4 or 5 years, that's going to negate any savings you're going to see. So you want to make sure you've got a sound warranty on that. And the same thing with the tanks. You can save money on tanks by buying cheaper tanks. Generally speaking, we see the cost-benefit working out to buying basically a tank that's the same quality of one of the better tanks that you can find in a home improvement center. So like an 8-year warranty, 8 to 10-year warranty. Anything less than 5 years, you're kind of asking for a lot of cost and a lot of hassle to replace the tank often. When you get out beyond 10 years, the tank prices tend to get very, very, very high. And it's my belief that the water quality in a homeowner's house is going to impact that decision more than the tank itself. If you've got very, very corrosive water, going to a higher quality tank may be justified. But you've got to read the warranties pretty carefully, because when the tank comes out, if you've got a $2,000 tank and it fails in 10 years and you pull it out, a lot of these warranties won't cover it if you've got lots of sediment built up in the tank. So if you've got lots of minerals in a well that's not treated properly, and the tank fails, and you pull it out, and they open it up, and they find this buildups, that may not be covered anyway. So you've got to be careful. When looking at life cycle costs, maintenance requirements are also key. So some systems require for the warranty to be honored that the heat exchanger fluid is changed every year or other year. The fluid is generally somewhat expensive. It's in the $30 to $40 per gallon range for the glycol. So the two factors you have to look at are how often does the fluid need to be replaced and how much fluid is in the system. If you've got a system with very, very large pipes to run the fluid back and forth, it's going to use a lot more glycol. It could be 5 or 6 gallons of glycol in some of the systems. Systems that use very, very small pipes use a lot less glycol. So that's something to factor in. Are you going to have a $200 or $300 expense every couple of years changing out glycol, or are you going to have a $50 expense every 10 years changing out glycol? So that's something to look at. And then finally, parasitic power loss. Some of these systems are powered through 110 power out of the wall, and that power doesn't come free. A lot of times when looking at the system performance characteristics, that power isn't taken into account. So that's actually reducing sort of your overall home efficiency a little bit. It's not a lot of power. Most of these systems draw probably 50 to 75 watts when they're running. So it's not a lot of power, but it is a factor, and it should be considered. I'm pointing this out here because most homeowners themselves, in my experience, don't really look at life cycle costs at all when making these investments. Initial purchase price tends to be the driving factor, and it really takes a professional, either their architect, their systems installer, to kind of point out the fact that going with the initial low price, in most cases, is not the smartest way to make these investments. Well, this lesson is one that I don't like, but it's true. And I think that the people who do insulation and ceiling have the same problem. These just aren't sexy. And putting in something to heat your hot water in your house, for some reason, just doesn't tend to appeal to most people, present company excluded. It looks like a tank and a bunch of pipes in your basement, and that's what it is. What we found is that, and my recommendation on most of these systems is to keep it simple. The simpler the systems are, the longer they last, and in general, the better they work. Unfortunately, from a marketing point of view, a lot of times adding sort of some flash and dash makes things sell better. And if you look at photovoltaic systems, I think a large portion of the high adoption rate is, hey, they're really shiny on the roof. A lot of the inverters now have got some really nice dials and LEDs and stuff, so people get kind of excited about them. These systems simply aren't sexy, so they don't sort of sell themselves, but they work. I mean, they work really, really well. If you buy a good system and it's installed well, it's going to work for 30 years. It's going to continue to save money for 30 years. And it's a pretty sound investment in almost any scenario. So it's our job, I think. Part of the reason I'm here is to try and make sure that more of these systems get installed in homes, because they're just the right thing to do. And it may well be that it works so well that people just don't believe that the sales pitch that it's saving that much money. Particularly in New England, I find a lot of times people don't believe that you can make any hot water when it's cold outside. They just don't. They don't understand the physics. They don't believe it. And so the monitoring data is very convincing. And holding their hand under a pipe that's been heated in February is convincing as well. As I said, I talked about it before. Single tank solutions look great. They're really tempting from a mechanical point of view, but we find that you're basically compromising on the single best efficiency, sort of most productive efficiency improvement you can make, which is get as much storage as you can have. And I've covered all that. Since a lot of passive homes are smaller, we have found is that you don't always have to. It's much better to go with two 40-gallon tanks, one for electric hot water heating, one for a solar storage tank, than it would be to go with one 80-gallon tank with a resistive element on the top and a thermal siphoning running into it. And so we found is going to the sort of what the industry calls the low boy tank. We can actually get these installations done in crawl spaces and sort of under landings and stairwells and things like that. So just because you don't have a lot of space doesn't mean the solar hot water system isn't going to work for you. If you don't have a dedicated utility room, a lot of times if you're creative and can carve out just a little extra space, doesn't even have to be full height space, you can get a solar hot water system into the home. Your plumber might not thank you. It may be a little bit difficult to sweat those last couple of joints, but it is possible. Another thing to think about is that components have got to work as a system. For these to work, in some cases, for them to work at all, not even to work well, you've really got to make sure that the components you're using, primarily the collectors, the heat exchanger, the pump, and the tubing that go back and forth, they've got to be designed to work together. Primarily because what you're looking at is heat transfer both in the collectors, how quickly are you going to be putting heat into your heat transfer fluid, and then your heat exchanger, how quickly are you going to be pulling heat out of it. So I'm absolutely not saying that you have to use components all of the same brand, but when you're looking at a system, if you're not buying a pre-engineered system, you've got to take the time to look at what how these components were designed to work most efficiently. What flow rates are they designed to work at? What temperature gradients are they designed to work at? So if you're going to mix and match and pull a lot of different catalogs, you certainly can do it, but don't do it blindly. You've got to do it with the specs in mind. The other thing to think about is that maximizing the theoretical thermodynamic efficiency isn't the goal in these systems. So you'll see a lot of systems saying, hey, you know what, we've got a 95% efficient collector, or our total system is 90% efficient when everything is good. That is important, but what you really want to look at here, efficiency is, we're used to thinking about efficiency as being important because fuel is so expensive. In this case, the fuel is completely free. So what you really want to think about is how many BTUs are you producing per your dollar invested over the life of the system. And if I could sell you a $2,000 system that was only 20% efficient but covered all of your needs, well, I mean, it may take a lot of collector area, but if it was inexpensive and it was going to last the whole time, that's great. So you're wasting 80% of that solar energy. It's getting re-radiated or anything else. Well, I mean, who cares? You really need to look at how many BTUs are you getting per dollar invested. And now, that does tend to correlate with system efficiency because if I've got to have 5 times more collectors, in general, that's going to be more expensive. But looking at a system, one system that's a collector that's 92% efficient versus one that's 87% efficient may not make any difference if that 87% collector is going to last twice as long, or is going to be 30% less investment, or is going to allow the glycol to last 10 times as long. So that's something that's not immediately obvious, but thermodynamic efficiency isn't the goal. Water quality, probably most of the sort of dissatisfaction I've seen in these systems comes with homes that have not addressed sort of intrinsic water quality issues. On city water, I've yet to see this be a problem anywhere. But with well water, there's very, very high mineral content. What we're seeing is sedimentation in the heat exchanger and in the storage tank at a pretty rapid rate. Now, our maintenance instructions require homeowners to basically flush their storage tank every 6 months. That's no different than the owner's manual in, I think, every electric hot water heater sold in the country, or hot water heater. But very, very few people actually do it with their hot water heaters. We really encourage our dealers to kind of beat the customer over the head and say, hey, look me in the eye, you're going to flush this every 6 months, right? And what I tell people when they ask about why it's true, if you flush and you find out, hey, I get 1 or 2 grains of sand every 6 months, you may be able to go to every year. Now, if every 6 months it has to run for 15 minutes before you get clear water, you probably ought to be doing it every month. And the whole goal here is to make sure that you're not allowing sedimentation to build up. Because as soon as it builds up in the storage tank, particularly in a thermal siphoning system, you're going to stop the thermal siphoning action. The system simply won't work. Whereas on a fossil fuel water heater, electric water heater, the system still works. You just get less and less capacity over time. So it's critical that they're flushed. And I've already kind of covered snow shedding. So we've learned that. The one thing we have learned, fortunately not directly, but from our manufacturing partner, is you got to make sure people aren't using metal roof rakes in the winter to clear these systems. The tip of a metal roof rake will crack the glass on these collectors very, very quickly. I can't speak to evacuated tubes, but I would imagine they don't like metal roof rakes either. And it's amazing how many people just feel compelled to get out there and clear the snow off. If you have a site where the person said, hey, I want to make sure I'm making as much energy as I can, even in the wintertime, even in blizzards, strongly advise them to get a ground mount system and use a foam brush to clear the collectors. That's totally fine. Same type of brush that they use to clear cars on the car dealership lot. If it doesn't scratch the paint on the car, it's not going to hurt the collectors. Okay, so those are kind of some of the installation and operation lessons learned. I'll talk a little bit about the performance data that we've seen over the past year in 2 homes that are in Charlotte, Vermont, which is about 15 miles south of us. These were both homes that were built by Habitat for Humanity. They're relatively small, passive homes. Snyder was highly involved in them. Chris, you may have been involved in them as well. I don't know if you were. No? Okay. My involvement goes back to the monitoring of them, working with Efficiency Vermont to design the monitoring systems for the whole house energy package. And you can see this is one of the pages that we created for one of the homes. This is a snapshot I took this morning. And it basically allows us to look at the system temperatures in the solar hot water system, and it calculates how much energy the system is generating from the solar system, how much of the solar hot water energy you're using on a given day and month, and how much total domestic hot water energy that the house is using. So you can start to calculate what % of your domestic hot water load is covered by your solar hot water system. So as I mentioned, we're going to look at 2 homes. These houses are literally 200 feet apart. They're similar in design. They're very similar in size. The solar hot water systems on them are identical. So the only real difference you're going to see between these 2 are the residents and how they use their systems. And as you'll see, it's incredible how differently the systems perform and what the different residents are getting out of the systems based on their usage patterns. We'll look at what I'll call the low load home first. This home was occupied last year, so I think they've been in it about a year and a half, probably a year last July, I think is when they moved in. Generally 2 residents there. I think they have some guests, but they have very, very low hot water usage. So far in 2012, I went back and looked at the first 9 months 2012. Their average hot water use is 37 gallons a day. Our typical customer is 4 people in the house and is using 55 to 60 gallons a day. So they're using a little bit more than half of a typical home, which the system is sized for, with 2 collectors and an 80-gallon storage tank. The home is on the right. You can see the 2 solar collectors up on their roof. And their basement is on the lower left. And you can see they have the large tank to the right is the solar storage tank. The tank to the left, immediately to the left of that, is their conventional electric hot water tank. And there's a pressure tank to the left of that. So a typical installation. And so this is what we've seen so far this year for their load data for their energy usage. This is BTUs. Is the scale on the left. The red bar is how much energy they needed to heat all the hot water they used that month. The green bar on the right is how much of that energy was provided by their solar hot water system. And as you can see, unsurprisingly, in January, February, and March, the solar hot water system didn't make all of the energy they needed. Hence, they need a backup system. But as the days got longer, the fraction that was provided by the solar hot water system increased each month. And the percentage went from a low of about 25 to 30% in January, and by March we were up at about 80%. Once we got to April, we were providing almost 100% of their energy needs every month. And when we get into July and August, we're producing more energy than the home is demanding. And so that overage is explained by basically standby losses. So we're producing a lot of energy. The house, they're simply not using all that energy. It's not coming out of the tap. It's just the system shuts down and the tanks cool down in the basement. And so that extra energy is just radiated out into the basement. Once we got into September, we're seeing the energy needs not quite met by the solar hot water system once again. So this is about what we expect. So far this year, the solar hot water system has covered, I think, 87% for her energy, domestic hot water heating energy needs. That's a higher figure. As I said before, we generally calculate 65 to 75%. There's two factors here. One is I don't have a full year of data on this. In October, November, December will be lower. So her figure will probably drop down to about 80% by year end. The other factor is she has more system than she needs. So as you can see here, in July and August, we were generating quite a bit more power than needed. So thank you. So with only 2 people, this house could have been served with 1 collector and a smaller storage tank. So they're a bit overserved. So their efficiency, their fraction has gone up higher than the average house. I did take a minute to load. We also have this home's electrical system monitored, and we can look at the home's electric hot water heater usage every month as well. And it tracks exactly as you would expect, with January and February being the highest usage months, where we're covering less than half of her need. And then in the summer, it drops down quite a bit. One of the advantages of monitoring these systems is you can sort of see, once you take a chance to look at the data, how to optimize the systems a little better. So when I looked at this data over the weekend, what I realized was that this home shouldn't be using any electrical energy from between May and September. And as you can see from here, we are using a little bit of electrical energy. And when I went back and looked at the photograph of the system that I borrowed from Peter's past home presentation, I realized that the system was installed with 2 mixing valves, a mixing valve in the output of the solar hot water storage tank and a mixing valve on the output of the electric hot water tank. One of the things we've learned with monitoring is that level of tempering is not necessary and it's unproductive. So one of the recommendations we'll make is to remove that sort of intermediate mixing valve. As long as you've got a functioning mixing valve on the output of your backup hot water heater, there's no need to have that second mixing valve in there. So that's a change we made. That's going to increase our savings a little bit. The other thing the primary thing that it will allow that homeowner to do is it will put much, much hotter water into her electric hot water heater, conventional storage tank. So she can actually then throw the breaker on it and not run it all summer. So when she's putting water in at 160 degrees, even though she may have a day or two where she doesn't use it, it'll drop 10 to 15 degrees a day, but she'll continue to have hot water and it'll continue to be replenished as she uses it with 160 degree water. The mixing valve is going to dump in 130, 140 degree water. And so therefore, if she has a couple days where she doesn't use water, it's going to cool down to the point where it may well be uncomfortable. And so she's going to want that electric hot water heater on. So by getting rid of the mixing valve in between the two, it allows truly unassisted operation throughout the summer months to become much, much more viable. Okay, so this is a house with very low demand, and you might think, okay, well, I mean, any system's going to look good if you don't use it very often. But the truth is actually, the systems tend to look much, much better the more hot water you use. And by happenstance, we happen to have a house next door whose residents use a lot of hot water, almost as much more than average as she uses less. So the study number 2 is about 250 feet south of home number 1. So it gets the same exact climate data. We're using the same system. The only difference we made is we ground mounted these panels primarily because we wanted to. This is our. We own this system actually, but we're allowing the people who live in the home to benefit from its heat. And we wanted to be able to really study this system carefully, monitor the collectors a little bit more thoroughly. And so by mounting them on the ground, it allows us access to them. We put the collectors in. We put the collectors in June. The system was actually cut in July, and got the monitoring on the solar hot water system going in August. So this data is pretty fresh. I really only have one complete month's worth of data. The home's got 3 residents all the time, but frequently have guests that bumps it up to 4 or 5 residents. What I found is for the month of September, their average hot water usage is 108 gallons a day. So this house is using 3 times as much hot water as the house next door. So this is their daily hot water usage. It's kind of busy. Like I said, I couldn't aggregate it because we only have 1 month's worth of data. But the chart is set up the same way with their total domestic hot water usage on the left in red and their solar hot water usage on the right in green. And as you can see, most days we outstrip demand with supply. Toward the end of the month, there was a couple days where the monitoring system went offline, so I don't have those days. But I continue to have data. So on aggregate, we've got 81% of the total energy needs covered by solar. Those last couple days in September, the 25th through 27th, were very cloudy and rainy. So if we had that data, what you would see is the red bars would be pretty high and there'd be almost no green at all. So we were running up in the low 90s up until then, and then that last week in September, we ended up having to run the electric hot water heater substantially. But even in this high load home where we're using 3 times as much hot water, 81% of the domestic hot water energy came from the solar system. In the same month, on the house next door, 86% of the energy came from the system. So if you look at the scale here, we're producing on sunny days, generally speaking, 40 to 60,000 BTUs of energy on that system. The nameplate rating on the collectors is 30,000 BTUs per day. So they're producing nameplate rating most sunny days. If you look at the system next door, she was using anywhere from producing 15 to 20,000 BTUs per day. Now, if you didn't have the data, you might say, well, the system doesn't work. They're rated for 30,000. The problem is there's just no demand. So there was no demand. As I said, that house would be served with 1 collector. It would produce more than enough energy for their use. So, as I said, on average, this system produced 45,000 BTUs per day. There were quite a few cloudy days where it didn't. But on average, with cloudy and sunny days, this house produced 45,000 BTUs, literally twice the energy. I think the home next door was about 21,000 BTUs, so more than twice the energy of the home next door with the exact same climate and the exact same hardware. It's all use dependent. And the really nice thing is by looking at the energy monitoring, one of the reasons we went there is because Peter had mentioned to me that their electrical bills were very high and their domestic hot water heating was the biggest portion of their electrical bill. And so I went back and looked at what their electrical cost was just for the electric hot water heater circuit. And they were consistently running over $80 a month, March through May. We turned the system on in mid-July and immediately saw the bill cut in half. It was about halfway through the month. And then August and September, they saw their bill down in the $5 to $15 range. So we're seeing savings in the summertime of over $70 a month. It's made a huge difference for them immediately. They tried turning off the electric hot water heater. Their demand is so high that the system really couldn't keep up. They would be better served with 3 collectors and a 120-gallon tank because they could use all that heat. So it does make a difference. It makes a big difference. I think that's all I had for the data. Any questions about passive house, how we monitor them, how the systems work?
What is the increase in production in cloudy days with evacuated tubes? Because I've heard that that's their real power, that they do much better on cloudy days.
The question is, what's the increase in production on cloudy days from evacuated tubes? I've heard that too, but I've also read studies that show that there was a home in Ithaca, New York, where they mounted both, and they found over the course of the year, I think the flat plates actually did better. It gets fairly cloudy. Having spent 6 years, I can tell you it's almost always cloudy. They found their flat plates actually did a little bit better, but it was, when I looked at the data, I wouldn't call it statistically significant. It was a couple %. So I haven't seen the flat plates, the evacuated tubes. I wouldn't tell you that they do better on cloudy days than flat price. I haven't seen that data, but I've heard that sort of the common movement.
Do you have a ground mount system you mentioned you want to set up for the building? Sort of set a draw or deep draw or 0 to 100 feet.
Yeah, so the question was, we recommend keeping the ground mount systems within 100 feet of the home, and is it a BTU loss? And the reason we do that is absolutely that, because of thermal losses. We haven't done the hard calculations to look at exactly sort of how many BTUs or what % you lose per foot, but what we believe is that we, and I haven't instrumented any really long runs yet, but we believe you lose less than 5% going out to 100 feet. And while you could go further, we just find that it's not, we don't recommend you do it. You could, the system would run, if you really had to do it, you could completely overcome that by just adding another collector if you wanted to. And the collectors themselves, as part of system costs, are fairly inexpensive. They're about $1,000 a piece. When you're looking at the cost of the entire system, it's not that much. So it's completely driven, at least in our system, by thermal losses. You could also simply insulate more. So that's the other thing you could do. Remember, we insulate with about an inch armor flex around the copper tube. You could, I think it's a 1 inch. Is it 1 inch thick? Sort of armor flex closed cell foam, which is pretty typical. That is around each copper tube, and then that's stuffed into a 3-inch conduit, which goes into the ground uninsulated. Some installers wrap that 3-inch conduit with additional insulation. That's going to help as well. So if you've got to go further, you could either add more generation or you can insulate better. As I said, the right answer is what is more sort of cost-effective for BTU, and it may well be just a bit more generation capacity.
Is that the same insulation you use on rooftop systems?
Exactly. Any other questions? Okay. Thanks.
Okay. I wanted to thank Doug Merrill from Sunward Systems for coming and giving us a presentation today on not only the basics of solar hot water, but also the very interesting data on actual in-place usage for high and low usage and how the efficiencies work. I want to thank everyone who logged on for coming and seeing the presentation online. And I'm going to stop the phone call right now, so thank you. And we are going to be posting the recording of the webinar online in the next couple of days. So if you're a member of the Alliance, you can go to the Passive House Alliance US website and go to the members area and see that presentation. Thank you very much.